Many of the things that we know about electron structure we learned by studying different things with light, and one of them has to do with the wavelengths of light emitted when a gas is heated. We're going to look at hydrogen next week in lab. When you heat hydrogen gas using an electric current, you get 4 visible wavelengths of light that are emitted. And so let me explain the picture. This part is just showing you all the possible wavelengths of light and their color that are visible. And this up here is the hydrogen line spectrum, the emission spectrum for hydrogen. You only get very specific wavelengths of light. And so you guys, this is like you have it looks like a fluorescent light bulb, but it has hydrogen in it. And when it's heated, if you look at the light, you only get these wavelengths. And we'll do that in lab. So anyway, if you get 4 different colors, that means you have 4 different energies of photons or light emitted. So we're going to look at how electronic structure can make sense out of that. So let's go on and look at the electrons, and we'll get back to how that has to do with the light. Okay, so we're going to go through some simple Bohr's postulates about electronic structure. Electrons can only have specific energies, and we call these principal energy levels. In other classes, you've probably called these shells, or maybe just plain energy levels, which I will say energy level a lot. The energy of an electron at an energy level is given by this equation, and this N stands for energy level, principal energy level right here. So this is the energy of an electron, and this RH is this Rydberg's constant for hydrogen. It's different for it would be different for different elements. And then of course the energy level squared. So anyway, that's the equation. We'll be using that quite a bit in lab next week. Okay, so we have specific energies that are allowed for electrons to have. But electrons can make a transition between those energy levels. They can, if they absorb energy, they can increase, go to a higher number, higher energy level, or if they emit, they can decrease. They're in. So when we say increase in N, that means like going from the first energy level to the second energy level. That's what we're talking about. We'll look at it graphically. Let's see. Okay, and I'm going to back up a little bit and talk about a simple Bohr model that you've probably drawn before, and then talk about the fancier way of thinking about it. So I'm going to start just by looking at this one. It's not erasing for me. So on this one, this is our simple Bohr model, and you've probably learned this way, the nucleus in the middle, of course, and then we had these rings surrounding that, and those we might have called shells, but those are what we mean by energy levels. So this is like N equals 1, N equals 2, and they do go out like that. And then let's see, you probably learned that if you're going to show where the electrons on here, you would start with the inside and you would put 2 there. And then if you had more electrons, you'd go to the second energy level or second shell, and you could add there, and that one had a limit too, didn't it? You could put up to 8 on that one, And then if you had more than that, you would go to the third, and so on. So just a couple of things. So we say that the first energy level, the inside one, that's where you put them first. Why is that? It's because that's the most stable energy level, the lowest energy level. It's close to the nucleus, and electrons are attracted to the nucleus. So that's the lowest energy place for them to be, most stable place to be. But why didn't we just put them all on that first energy level if that's the best place? Because only so many will fit. Electrons repel other electrons, and so they won't all fit there. They start repelling each other. Notice that as you move out, you could put more, the number you could fit got bigger and bigger. And it's because when you get further from the nucleus, there's more space. You know, each energy level actually occupies more space. So anyway, this model, it is a simple model because they don't really look like this. You don't really have orbits, but it does give you a way to kind of think about what's going on. So this is a little bit fancier way of seeing it, just an energy diagram and not trying to show the shapes because the shapes are different. So as an energy diagram, again, this is low energy down here means most stable. And up here, it's the least stable. I should just say, yeah, well. Okay, and so what we were saying about electrons making a transition, if an electron is in the first energy level and is excited up to the third energy level, it's going to absorb energy to do that because it's less stable. And this is what happens when you heat the hydrogen, is that it absorbs some of that energy and the electrons are excited up to a higher level. They won't stay there though because that's less stable, so they'll drop back down. And when they drop back down, they're going to release energy, and they do that as light. One packet of energy, a photon. And that photon will have all of the energy that was lost. It doesn't go into multiple ones, just one packet of light. So how much energy is in that packet depends on where it falls from. You know, if it fell it may just fall, oops, not up there. It may just fall one step up here, and that packet of energy would have less energy. Now, if it fell just one step, it would go ahead and fall. It could fall more. It might do it in steps, but each step that it falls, it only releases one packet. And yeah, definitely it could fall all the way and release a very big packet of energy, which means a high energy photon. Okay, I wanted to show you this over here. So this equation is the equation for calculating the energy of an electron on an energy level, where RH is that constant, and RH is a positive number. So when you calculate this will be a negative number, and of course N is energy level. So for this one, the energy would be just negative RH. Okay, it's kind of weird that they're negative. Let's write that down. Because when you do your lab assignment, you'll need to make sense out of that. Be sure you have negative numbers for those. So it seems kind of weird. It's not really that they have like the alternate or the opposite of energy. It's just a matter of where we assign 0 and that these are more stable. If you want to consider this, so I'm going higher and higher in energy levels, and the highest I could get would be N equals infinity. And N equals infinity would be where the electron has left the atom. Okay, and what would the energy be there? It would, let's look at energy. So energy at N equals infinity would be negative R. Okay, and so that number would approach 0. Let me get a different color. So at n equals infinity, let's just put it right here. Okay, and that makes sense because once the electron has left the atom, it no longer has any potential energy to do with its attraction to that atom or that nucleus. Okay, and so if you accept that this number up here is 0, then these numbers have to be negative because they have less energy than this 0. It mathematically works out to where if we call this 0, which makes sense, that these have to have negative numbers because they're lower energy than 0. They're more stable than that one.